Sugarcane. Did you know that you can transform sugarcane into ethanol, the alcohol which is very useful in our daily activities? Here is the process. It is simple and possible. Preparations of alcohols. The first preparation method is preparations of alcohols from alkyl halides by substitution reactions. Alkyl halides, when refracted with aqueous alkali, like sodium hydroxide or potassium hydroxide, or moist silver oxide, which is forming silver hydroxide, these produce alcohols. The hydrolysis occurs by nucleophilic substitution reaction. An example: 2-bromo-2-methyl-betaine reacting with potassium hydroxide in water under reflux will produce 2-methyl-butane-2 or potassium ion and bromide ion. Let us have the mechanism. Here is 2-bromo-2-methyl-betaine, a tertiary alkyl halide. Because of inductive effect within this molecule, when it is dissolved in a polar solvent, it ionizes to give a carbocation and bromide ion. This is what we call self-ionization. The carbocation formed has a positively charged carbon which is octet-true unstable, and this positive charge attracts electrons from the hydroxide ion, and they form a dative covalent bond which will result in the formation of an alcohol molecule which is more stable compared to the carbocation. And this is what we call nucleophilic attack of hydroxide on the positively charged carbon of the carbocation. Energy profile diagram. Here we have two axes, one representing the potential energy, another representing the reaction pathway. As it is for all chemical reactions, we start with the reagents at a given energy level, and during the reaction process, the energy may rise and fall until it forms a stable chemical species which are called the products. But during the reaction pathway, there is formation of transition states. The first transition state is formed where the carbon-bromine bond will start to break, and this will result in the formation of carbocation, which is again going to absorb some energy and reach to another transition state, which is the second transition state, where the carbon-oxygen bond will start to form. And after that, the stable products will be formed, which is an alcohol. This reaction happens in two steps, and we want to know which step is the rate determining step. Let us compare their activation energies. Here we have two activation energies as we have two transition states, and which activation energy is higher than another. You can see that the first activation energy is higher than the second activation energy, which means that the first step is slower and higher in atomic compared to the second step. So the first step is the rate determining step. So the rate of this reaction will depend on the concentration of the alkyl halide only, because it is the one which is involved in the first step. So the name of this mechanism, it is SN1, or unimolecular nucleophilic substitution. Activity. Explain the mechanism of the following reaction. Draw its well-elaborated potential energy diagram. Hence, deduce the type of mechanism, SN1 or SN2. Feel free to pause the video and try this activity, and after, continue with the lesson. The second method consists of preparations of alcohols from alkenes by addition reactions. Alkenes react with water in the presence of sulfuric acid under hot conditions to form alcohols by electrophilic addition. If the alkene is unsymmetrical, the addition respects Markovnikov's law. Example: propene react with water in sulfuric acid under hot conditions. It will produce a mixture of alcohols, 1-propanol, which is a minor product, and 2-propanol, which is a major product. This is explained by Markovnikov's rule, which says that the proton is added to the carbon atom with the highest number of hydrogen atoms attached to it. In other words, the rich gets richer. It is explained by saying that in the ionic addition of an symmetrical reagent to a double bond, the positive portion of the adding reagent attaches itself to the carbon of the double bond so as to yield the more stable carbocation as intermediate. We can use the mechanism to explain Markovnikov's rule. The hydrogens in sulfuric acid are highly labile and highly electron deficient due to the negative inductive effect of oxygen. The positive charge of hydrogen attracts electrons of the double bond, and this adds on one of the carbons, and another carbon acquires a positive charge. Depending on the carbon which has acquired a positive charge, we will have a mixture of carbocations, primary and secondary carbocation. The secondary carbocation is more stable than the primary carbocation and it is much abundant in the mixture than the primary one. That's why in our next step we are going to continue with only the secondary carbocation. The positive charge on carbon is going to attract electron from the nucleophile, which is water here, and there is a formation of a dative covalent bond between oxygen and the carbon, which will result in the formation of oxonium ion. The oxonium ion is not stable because there is a positive charge on a very electronegative element, which is oxygen. That's why any base in the mixture, and here water can do the job, subtract hydrogen from the oxonium ion, and this forms an alcohol and a hydronium ion. Note: alkenes in the presence of aluminium oxide react with water to form alcohols in vapor phase, then condense to give liquid alcohols, as it is shown by this example. Hydroboration oxidation of alkenes. Alkenes react with the boron hydride together with the hydrogen peroxide and a strong aromatase base to produce an alcohol. This is an anti-Markovnikov hydration of alkenes. The general equation. This happens in two steps. The first step, it is addition of boron hydride in tetrahydrofuran, and the second step, it is the reaction with the hydrogen peroxide in a basic medium. Let us have these examples. Propene reacts with boron hydride in tetrahydrofuran to give the first product, which is then going to react with hydrogen peroxide in a basic medium to give an alcohol. Here the major product is different from the major product predicted by Markovnikov. As you can see it, the hydrogen was added to the most substituted carbon, or the carbon with fewer hydrogen atoms, while it was supposed to be added to the carbon with many hydrogen atoms as it was predicted by Markovnikov. So this is the anti-Markovnikov. The fourth methods consist of preparations of alcohols from hydrolysis of esters. Esters are heated under reflux with the dilute acid such as dilute hydrochloric acid or dilute sulfuric acid. This reaction produces a mixture of alcohols and carboxylic acid. An example: an ester reacting with water under hot conditions with sulfuric acid gives a mixture of ethanoic acid and ethanol. In order to favor the production of this reaction, the production of ethanol, you will need to use excess water because the reaction doesn't go to compression. Another reaction is the hydrolysis of esters in basic medium. Esters undergo hydrolysis to yield alcohols and salts of carboxylic acid. This reaction is known as saponification. Here the ester reacts with water in basic medium to give ethanol and a salt of carboxylic acid. And this reaction is not reversible. That's why this may be a good method of preparation of ethanol than the previous one. The fifth method consists of preparations of alcohols from aldehydes, ketones, carboxylic acid, and esters by reduction. When aldehydes and ketones are reduced in the presence of suitable reducing agents like lithium tetrahydroaluminate in dry ether and then water, or sodium tetrahydroborate in water and ether, or molecular hydrogen with catalysts like platinum, nickel, palladium, they form primary and secondary alcohols respectively. That's to mean ketones produce secondary alcohols, while aldehydes produce primary alcohols. Carboxylic acid are reduced by lithium tetrahydroaluminate or sodium tetrahydroborate or potassium tetrahydroborate by hydride attack specifically on carbonyl group, followed by hydrolysis using water. Or they are reduced by molecular hydrogen under the catalyst to produce primary alcohols only. Esters are reduced by strong reducing agent like lithium tetrahydroaluminate, not sodium tetrahydroborate, to produce primary alcohols only. That is to mean esters are not very reactive as the previous ones, so they cannot be reduced by weak reducing agent like sodium tetrahydroborate. Examples: a ketone reduced to a secondary alcohol, an aldehyde reduced to a primary alcohol, a carboxylic acid reduced to a primary alcohol, and an ester reduced to a primary alcohol. Thank you.